sine function. Let me first of all point out something that it's not a mistake, but I kept telling you that my scale was pretty bad, and I wasn't sure exactly where my scale was bad. Pi over 2 is about 1.5, right? So if you look at what I labeled as 1, it should be like 0.5, right? In terms of my scale. So that was my, and also the height of the sine curve. This height here should also be like 0.5, because but my scale was really pretty bad. So I just wanted to start out with drawing a nicer version of the picture. And so again, in this picture I have the sine function between, the green one is the sine function between negative pi over 2 to positive pi over 2. And then between negative 1 and 1, I drew the graph of the inverse sine function. Okay? And this time my scales are much better. Of course, still there are some problems with the scale, but that's like the I can live with that, but I couldn't live with the other one, so that's why I made this one. Okay, so any questions on that? There wasn't any mistake, it's just the scaling was pretty bad. Okay. Alright, so just wanted to remind you that the graph of cosine function between 0 and pi is a decreasing function. The graph of cosine function between 0 and pi is a decreasing function. Because it is decreasing, it is 1 to 1, so it has a inverse function, and that's what your assignment was all about on the inverse cosine. So I won't say any more than that. Here's an example. So I think we did an example where we looked at the integral. Am I correct? The last example was the integral of 1 over root 4 minus x squared. Okay. So generally speaking, so last time what we saw was that if I look at the integral from integral of 1 over root of 4 minus x squared dx, and the answer we got was what? Sine inverse of half x plus c, right? Generally speaking, in general, I don't even want to call that a theorem, but if you want to remember it as a, well, let me not even call it an example as well. Let me just say this is a formula, but you don't have to remember it if you know how to derive it. This is 1 over a squared minus x squared root of that dx. That is equal to, can anyone guess what I would have within the parenthesis here? X over a, very good. Note that in the example I had a 4. 4 is like 2 squared, right? 2 squared, so that's why I have that half there. If I have a, that's what you're going to get. Now from this, can someone tell me what does it imply for the integral of 1 over 3 minus x squared root of that? What will that be? Sine inverse of x over root 3, right? Plus a c. Now, the formula in red, how would you derive that? A is a fixed number there. So you're going to do a u substitution, right? What did you pick for u? Oh, yeah, you're going to do a u substitution. What would be u? Let me go to the red one. So how would I derive the red? Yeah, you take you take x to be au, right? So that means you take u to be 1 over ax, right? Is everybody okay? So the substitute, remember the goal is to sort of get rid of that a squared and replace a squared with 1, and then I know that the antiderivative is sine inverse, right? So you do the substitution, u equals to ax, and that would tell you that du is a dx, and also this is going to tell you that x is 1 over a u, right? Is everybody okay? So then if I do that substitution, my integral 1 over, let me write that down again, a squared minus x squared dx, this would be the integral of 1 over a squared minus, remember you're going to replace x by what? Oh, I'm sorry, I made a mistake here, sorry. What am I thinking? Did you guys see that, the mistake that I made? What I want is the other way, right? I want x to be a times u, which means u is 1 over a x, and it means that dx is equal to a du. Okay, so that's what I actually wanted. So in the denominator, I'm going to replace x by au. And I have a times du is dx. Okay, and then this is equal to the integral of 1 over a squared minus a squared u squared times a du, and this would be equal to the integral. Remember, the entire point was to introduce a squared as a factor of x squared. If I did that, then I can factor out a squared, and this would be 1 minus u squared a du. And now you can see that root of what's the root of a squared? The root of a squared, well, let's just assume that a is positive, okay? If I assume a is positive, root of a is just a, and then I have 1 minus u squared, I have root on it a du. So what I'm doing here is that I'm assuming a is positive, okay? Otherwise the square root of a squared would be absolute value there. So this is the integral of 1 over 1 minus u squared root of u du, and that is sine inverse. That is sine inverse of u. And then finally, we know that u is x over a. Okay. Is everybody okay with that? So in this formula, you need to assume a is positive. Otherwise, it's not going to work out the same way. Right. Yeah.
If a was negative, wouldn't it just be a negative after becoming sine inverse?
Well,
Because when you cancel that a and a du, if it was negative on the bottom.
Okay, so generally speaking, A will not be negative. I can always assume A is positive because the number 4, the numbers like 4 is a positive, so you have to have a positive number there. Makes sense? If you had a negative 4,
so that it's 1 to 1. So that sign is 1 to 1.
yeah. So I mean, your 4 here, if it is a negative 4, then you couldn't do what we did. You have to do something else. Okay, so because of that, if 4 is there, then the square root of 4 would be 2. We are looking at the positive root of 4. That's 2. Okay. Okay. Any other questions? Is that okay? Because you have in front of, so you have something positive minus x squared. So whatever the positive, you can write it as a squared, where a is positive, right? So if it is 4, it's 2 squared. If it is 16, it is 4 squared, and so on. Okay, so this is sine inverse of x over a. And one more example that I want to go over is the integral from 0 to a fourth, the root of 1 minus 4 x squared dx. And in this case, this is 1 over, I'm sorry. This is 1 over 1 minus 4. So in this case, once again, it looks very close to the derivative of sine inverse, right? Remember, the derivative of sine inverse is what? The derivative of sine inverse is 1 over the root of 1 minus x squared. So it looks very close to the derivative of sine inverse. So what should I do to make it look like derivative of sine inverse? Well, the problem is that factor 4 in front of x squared, right? And the question is, can we make it look like 1 minus u squared, right? So if my goal is to rewrite that as root of 1 minus u squared, what would you pick? What substitution would you do? What's that? Say it louder. 4x to be u? Close. Let me make maybe one more line here. So this would be 1 minus 2x squared, right? So I should be picking u to be what? 2x. So if I pick u to be 2x, then I see that du would be 2dx, right? And dx would be half du, right? So dx would be, I don't have to write it, but okay, so this is equal to, I am replacing 2x by u, so I get this, and I am getting what is dx? That's half du, right? Well, that half, let's change the limits of integration. When x is 0, what is u? 0. When x is fourth, u is, what's that? When x is a fourth, what is u? Half. Okay, so I can take the half outside, and this is 0 to half. and I have 1 over 1 minus u squared left. And now we know this is half sine inverse of u, half and 0. And what is sine inverse of half minus sine inverse of 0? We did those exercises before. What's the sine inverse of half? Could you say that louder? Pi over what? Pi over 6, right? 30 degrees. Sine inverse of half is the angle for which sine value is half, right? So sine of 30 degrees is half, right? So this is pi over 6. And what is sine inverse of 0? Give an angle for which sine is 0, right? Sine 0 is 0, yep. And so I get pi over 12 at the end. Did everyone see that? You guys are okay with that? Yeah. Which half you said?
0 to 1 half. Where do we go?
So remember we picked u to be this, right? So this is the limits of integration for x. So when x is 0, you get u to be 0. When x is 1/4, you get u to be 2 times a fourth, which is half. Yep. And in the exam, I saw that some of you had mistakes, like you did the right substitution, you changed the limits of integration, but at the end you went back to x again. Once you change the limits of integration, you cannot go back to the original variable anymore, right? That's why you change the limits of integration, so that you don't have to go back to the previous variable. Am I making sense? So that mistakes, I saw that mistake made by a number of you, but it's not a big deal. It's just that keep that in mind in future, okay? Alright, so I think I'm done with my discussion with sine inverse of x. Okay, so now what we want to do is the general. Today, what I want to do is the general exponential function. So remember, you have to follow logically what we did. We defined the the natural log function, the ln function, as what? We defined the ln function essentially by saying that ln of x is the if x is bigger than 1, it is the, in terms of the areas below the graph of 1 over t, right? We looked at the graph of 1 over t, and basically we defined ln of x in terms of the area below that graph, right? Once we have that ln function, we then defined the exponential function as the inverse of that. And then we showed that the exponential function is in fact equal to the quantity e to the x, right? And then we defined e to the x as e to the x for when x is, we showed that e to the x when x is rational is equal to the exponential function. And then we said that, well, because of that, let's define the meaning of e to the x when x is irrational as the value of the exponential function. So now for us, e to the x and the exponential function, they are synonymous, right? Am I making sense? Now, so far I know what is the meaning of e to the x, but now I want to know what's the meaning of a to the x for any other number a. Okay? So general exponential means that so far we looked at, So far we looked at e to the x, and the e to the x is synonymous with the exponential function. The exponential function. When I say the exponential function, I mean the inverse of ln, right? So we said that e to the x is you can say that it is defined by exp of x. So basically we defined what is the meaning of raising a power when the base is e, right? But how about other bases? So that's what I want to do today. So let's let a to be greater than 0, and so now we are going to define a to the x. How? Well, a to the x, the meaning of that would be e to the power the same exponent x multiplied by ln of a. You understand that? We are saying that a to the power x, and this is for any real x, okay? This is for any x between negative infinity to positive infinity. So if a is a positive number, we are saying that the meaning of a raised to the power x is the same as e raised to the power x ln of a. Is this definition clear to you? Let's look at an example. For example, what is 2 to the power x? 2 to the power x is the same as e to the power x ln of 2. Okay? That is 2 to the x. Is everybody okay? Remember, we already understand what is the meaning of e to the something. That's the same as exp function evaluated at the exponent. And what's the exp? Well, that's the inverse of the ln function. Okay? Now, I haven't really told you how these functions are evaluated. How do you evaluate the exponential function effectively? I didn't say anything about that yet. But we'll talk about that later. So this is e to the x ln, but we know the graphs. Okay. Okay, so that's the example. So more generally, if I have okay, so let me say, let me make a remark here. Okay, so suppose that I have a function f of x, and f of x is larger than 0, and then I have another function g of x. So what would be the meaning of f of x to the exponent g of x? F of x to the exponent g of x. Well, the meaning of that would be e to the g of x, the exponent times ln of the base. You're okay with that? E to the exponent times the ln of the base. So that would be the meaning of this quantity. Of course, the base has to be positive. For example, what is x to the power root of x? Let me say, for example, what is x to the root of x? Well, I have to assume x is positive, otherwise it's not going to work. X to the root of x would be e to the power root x ln of x. Okay, that's the meaning of x to the root x. Are we okay with that? Okay, here of course I need x to be what? the base has to be positive. Otherwise, you cannot apply ln, right? You see that? In order to apply ln, I have to have something positive. Okay, so now the laws of exponents. Now remember, for the function for e to the x, the laws of exponents were what? For e to the x, the laws of exponents were e to the x plus y was e to the x, e to the y, right? E to the x minus y was e to the x over e to the y. Same exponents still work for a to the x. So here let a to be positive, b is positive, and x, y, both of them are just any real numbers. 1, a to the x plus y is a to the x, a to the y. 2, a to the x minus y is a to the x over a to the y. 3, what am I missing? ab to the power x is the same as a to the x, b to the x. Okay? Well, let me maybe prove one of them. Okay? So let's say proof of 3. Remember, when we prove this, we already accept that e to the these laws are already proved for the e to the x function. Even though I didn't really prove it for all of them, I proved it for probably one of them, and asked you to look at the other ones. So here I'm going to look at only the proof of 3. Why 3? Because it's the last one, it's in front of me, so I can easily, I don't have to rewrite that. So that's what we want to prove. So what is ab to the x? Well, by definition, ab to the x is e to the power what? E to the power x ln of AB. Okay, so now what is ln of AB? Ln of A plus ln of B. Well, what is that equal to? This is equal to e to the x ln of A plus x ln of B. But remember, I have a plus in the exponent. Remember, the laws of exponents are proved for e to the something, right? So then I can say this is e to the x ln A times e to the x ln B. But by definition, what is e to the x ln A? A to the x. What is e to the x ln B? B to the x, right? So what we have shown is that ab to the x is equal to a to the x, b to the x. And that's it. So we basically we based our proof on the fact that we have already proved them for e to the x function. Okay, and the others are just as easy to derive. Any questions? Do you guys need time to write this? Any questions at all? As usual, you have a new function. What do? What's the first question you ask? You ask what's the derivative, right? So what's the derivative of this a to the x function? What's the derivative? What's the derivative of a to the What's the derivative of a to the x? Now you need to base your calculation here on the fact that we already know the derivative of e to the x is what? E to the x. So what's the derivative of a to the x? What should I do here? What is a to the x? E to the x times ln of a. If you don't, what I'm going to do is rewrite this a bit and say I have e to the ln a multiplied with x. Now what is a? Fixed. What is ln of a? Fixed, right? So then what's the derivative now? Do I know the derivative of this? What I have is something like e to the power some function, right? How do I find the derivative of e to the power something? You did this in your exam. Yes, e to the same power, right? E to the same power times the derivative of the exponent, right? What's the derivative of the exponent here? Derivative of the exponent, ln a. Remember, a is fixed, ln of a is fixed. So think about ln of a being ln of 2. So you have some constant multiplied with x. So you're taking the derivative with respect to x, not a. So this is ln of a. You guys realize that? The derivative of ln a times x is ln a. ln a is a constant, x is the variable. You're taking the derivative with respect to x. But can someone tell me what is that again? That is a to the x again, right? Well, remember I said the e to the x is only one of the two functions for which the derivative is itself. For a to the x, it is almost there, but you have that annoying ln of a part here. So this is the derivative with respect to x of a to the x. Of course, here I am assuming that a is positive, right? Any questions on what I just said? That's the derivative formula. Yeah. Yeah, for any a. For any a. Do you want to remember that? Sure, if you can. If you don't want to remember that, that's fine too. You can always write a to the x as e to the x ln a and then just work with that. And that's what I usually do. Okay. You don't have to remember it, memorize it if you don't want to. But of course, if you can memorize it, that's fine too. Let me do an example. So let's say. So here's an example. What's the derivative with respect to x of 2 to the x? Well, if I know the formula, I know that this is 2 to the x times ln of 2, or maybe I am doing this after a couple of months, right? After a couple of months, and then I don't remember exactly what the derivative formula is. However, I do remember the fundamental definition that 2 to the x is the same as e to the x ln of 2. So if I remember that, I could say that the derivative is itself times the derivative of the exponent, which is ln of 2. And then I can rewrite that as 2 to the x. So this part is 2 to the x times ln of 2. Either way, whichever way you like, you could. Like I said, when you do math for a long time, you sort of you want to reduce the number of things that you want to remember, and so if I have to remember the definition, the fundamental definition of 2 to the x anyway, and if I remember that, I can easily come up with the derivative, right? So either way is okay. Now, here are a couple of questions that we want to ask. So we see that the derivative with respect to x of a to the x is a to the x ln of 2, right? Now, first of all, by the definition of a to the x, is a to the x a positive function or a negative? Can it have negative values? Remember, what is a to the x? A to the x, by definition, it is e to the x ln of a, right? Because remember, the function e to the x is a positive function. Yeah. It should be an a. Thank you. Okay, so a to the x by definition is e to the x ln of a. We know that e to the x function is what? Positive. The function e to the x is positive. Remember, the graph goes from 0 to infinity, right? Is everybody okay? So, does it imply that a to the x is positive as well? Yeah, because a to the x is e to the x ln of a. So no matter what the exponent is, e to the something is always positive. So a to the x is always positive. So now the graph of a to the x will be above the x-axis. Now, by looking at the derivative, if I know the sign of the derivative, that would tell me whether the function is increasing or decreasing, right? So notice, if I look at the derivative, if I look at the derivative is positive when? Positive on the entire domain, right? For any x. Let me say this a little bit differently. For any x between negative infinity to infinity, when is it positive always? When a is when a is greater than 1. Remember, ln of 1 is 0. On the left side of 1, ln is negative. On the right side of 1, ln is positive. So when a is greater than 1, I know that it is positive, and it's going to be negative when a is between 0 and 1. So what can I say about the a to the x function? When is it increasing? When a is greater than 1, it's increasing, right? So all this implies that a to the x is increasing on the entire domain if a is larger than 1, and it is decreasing on the entire domain if a is between 0 and 1. Is everybody okay? Any questions on what I just said? What would be the second derivative of a to the x? What's the second derivative with respect to x of a to the x? Well, it will be the derivative of the derivative, right? So it is the derivative of the derivative. What's the derivative? The derivative is a to the x ln of a. And what's the derivative again? Ln of a is what? Ln of a is constant, right? You don't need, I mean, you can apply the product rule, but the derivative of ln of a would be 0. So instead of that, this is just a constant, so I can take it outside, right? Or I can say that the derivative is, what is the derivative of a to the x? It is a to the x times ln of a, right? And then I have ln of a from before, right? You agree? Ln of a is constant, so that is there, times the derivative of a to the x. The derivative of a to the x is ln of a to the x again. So what do I have at the end? What do I have at the end? I have a to the x ln of a squared. Concavity, concave up or down? Does it depend on a? Concavity, does it depend on a? Concave up or down? We are not looking at the graph of ln, we are looking at the graph of a to the x. So we know that, remember, the concavity has to do with the second derivative, right? So second derivative of a to the x is given in front of you. What I'm asking, does it tell you anything about the concavity? What does it tell you? Very good. It's always concave up. Why? Ln of a squared, so that's positive. A to the x is always positive, I said, right? So a to the x is positive. Ln of a squared is positive. So together it's positive. Well, this is for any a, right? There is no condition on a. No matter what a is, it is always positive. So this is positive for any x between negative infinity to infinity, and doesn't depend on a. So that means that a to the x is concave upward on the entire domain. Can someone tell me what is a to the 0? A to the 0 is a to the power 0 times, not a to the power 0 times. It is e to the power 0 times ln of a, which is e to the 0, and we know that e to the 0 is 1. Why e to the 0 is 1? That's the inverse of log. Ln of 1 is 0, right? Ln of 1 is 0, so e to the 0 is 1. Everybody is okay with that? Let me use a parenthesis here. So a to the 0 is 1 as well. And what would be the graph? Well, let me just stop here. I have to give you your exam back, okay? Well, you guys should think